Welcome back. This is lesson 5 of my series on difference equations. In the previous lesson, we solved second order equations by guessing a power, if you recall, lambda to the n, and turning the difference equation into a polynomial. But everything we did assume the right-hand side was 0. That's the homogeneous case. In this lesson, we put the right-hand side back when b of n is not 0. The equation is called non-homogeneous, as we know, and it is the last piece of the linear theory. The way we solve this is breaking the problem into two parts. One is called the complementary part, and that's the homogeneous part of the equation, and we solve that as we had done before. And then there's a particular solution where we put the b of n back in and find a particular solution there. So that's what we're going to do in this lesson. So where are we? In lesson 4, we solved second order linear equations, but always with a 0 on the right hand side. In other words, this b of n term. A non-zero b of n makes the equation non-homogeneous. B of n is known as the forcing term. It stands alone, multiplying no member of the sequence. We met with the idea in lesson 1. Now we learn what to do about it. So here's the general linear case, I should say. None of the x terms are raised to a power other than 1. But now we have the coefficients or functions, and the forcing term is also a function. So as I mentioned in the first slide, what we first did was solve this where b of n is 0, and we get a solution for that. And then we find a particular solution when we put b of n back in, and then we combine the two parts to get a complete solution. So we'll go through the general procedure in a little bit more detail, and then I have 2 examples in this lesson. And again, we'll focus mostly on just second order. This is order k. When the same technique works, there's just the polynomial that you get from the homogeneous part is harder to solve. So here's the general structure of our problem, a solution to our problem, where b of n is not equal to 0. We do 2 things. First, we solve the homogeneous version where we set b of n equal to 0, and we get that solution. We know how to do that from a previous lesson, and we call that y sub n. And then we find a particular solution when we put b of n back in. Now, it needs not to be a multiple of the complementary solution. That's where you can run into a problem, and I'll explain that as we go through the example. Typically, you can just multiply by n and get something different from the complementary solution. Okay, so let's look at this. We know how to do this part. We don't know how to do this part yet, and I'll describe. There's different standard solutions, I guess you would say, that you would try in different cases. And I have a table that'll show you those. So here is the methodology in a little bit more detail. So first we solve the homogeneous equation, set Bn to 0, and use the characteristic equation from lesson 4. This gives our y sub n with arbitrary constants. Then the second part is the particular solution. Guess something with the same shape as Bn, substitute it in, and solve for the coefficients. This gives us z sub n. So I'll give you a chart or a table for what to guess based on what b of n is. So that'll be helpful. And the table is fairly comprehensive. It covers a lot of different cases. Then we add the 2 together. That's the general solution. Only now apply the initial conditions to the sum, never to just the y sub n. Okay, and we'll see this, and actually I have two examples, so we'll see this. Concerning the particular solution, we use a method known as undetermined coefficients. That's just a fancy name for taking a guess. We guess the trial solution was the same shape as b of n, but with unknown coefficients. We substitute it into the full equation, collect like terms and match both sides. The coefficients drop out. So why is guessing respectable? We only need to find one solution, and we are free to find it however we like. Once a candidate satisfies the equation, it is a solution. How it was found does not matter. So our method of guessing is a valid approach, and as I promised, I'll show you a table for what is advised to make a guess. Sometimes it doesn't work and you need to make a small modification, and we'll talk about that too. Okay, so here's the table I've been mentioning. For b of n, if it's a constant, then you would try a constant. We'll just give it a different name, but it's constant. Then if it's r to the n, we would use a constant times r to the n. If it's sine of c of n or cosine c of n, we just take a linear combination. Even if it's just one or the other, we still use both. It's a linear combination. If b of n is a polynomial, and I should have said r, yeah, r is a constant. I did mention that. If p of n is a polynomial, then you would take another polynomial as your guess of the same degree. If it's a constant to a power times a polynomial, you just take this and you multiply by r to the n. Then if you have r to the n times sine cn or cosine cn, you take a linear combination of the two. That r of n is multiplied times both of these. Okay, so let's continue. There's a possible problem with our methodology that crops up depending on the particular b of n that we have in our equation. So if a term of the trial solution, in other words, the guess from the table on the previous slide, already solves the homogeneous equation, it cannot possibly solve the non-homogeneous equation. Substituting it, the trial solution, gives 0 on the left and b of n on the right, an impossible equation. The unknown coefficients cancel out entirely and there's nothing left to solve for. So how do we fix this? We multiply the trial solution by n before solving, and by n to the s power if the relevant root has multiplicity s. And this here is tells you what to check for basically. So for a constant or polynomial forcing term, again referring to b of n, check whether lambda equals 1 is a characteristic root of the, that's for the homogeneous equation. For a term containing r to the n, check whether lambda equals r is a characteristic root. For sine or cosine terms, check whether the same sine-cosine form already appears in the complementary solution. If the proposed trial solution, referring to this here, overlaps with the complementary solution, multiply the entire trial solution by n, or by n to the s if the corresponding root has multiplicity s. Okay, so we'll run into this in the second example that I'm going to show you. So that might make this a little bit more concrete when we get to that. So this is the first of two examples. We have our difference equation. It's linear. You notice that each of the x terms is raised to the first power. It's not homogeneous, although it's just slightly off, right? We have a -1 here, so b of n is not 0. And it is autonomous because these are just constants. P and Q are constants. The initial conditions are x sub 0 equals 0, x sub capital N equals 0. And we also have these conditions. This comes from a probability problem. That's why these add to 1. P plus Q equals 1. P does not equal Q. And both P and Q are between 0 and 1. Okay, so the first step, as we've mentioned several times now, is to solve the homogeneous equation. And then we'll need to make a guess at this for the particular solution, which will just be a constant since that's what we have here. So, and I have a reference here. This comes from the gambler's ruin problem in my stochastic processes playlist. If you go to my channel and look for stochastic processes, and then you'll see a playlist for that, and then under Gambler's Ruin this problem appears there. But I don't really focus on the probability problem here because we have enough to deal with just understanding how to solve this in general. So let's continue on the next slide. So we solve the homogeneous part of the problem first, the complementary solution it's known as. So when we put in lambda to the n for x sub n, and lambda to the n plus 1 for x sub n plus 1, and lambda to the n plus 2 for x sub n plus 2, and then we factor out lambda to the n, we get this here. And we can factor that like we have here. So then we have one root is 1, and the other root is q divided by p, which we'll call r. And just made a note here, one of our conditions was p does not equal q, so this is not equal to 1, which means r is not equal to 1, and we have two distinct solutions. So the complementary solution is of this form here, a times lambda sub 1, which is 1, to the n, so that's just a, and then b times r to the n, so we get this here. Okay, so we're half the way there, and now we need to solve the problem where this is, we plug in the minus 1. That's the part you don't know how to do, or at least we haven't done an example of that yet. So we'll do that on the next slide. So we actually run into the problem I mentioned on this first example. You see here, we put in b of n equals minus 1. It's a constant. And the table tells us to try a constant a. But from the couple slides back, with the problem we mentioned, when lambda equals 1 is a root of the characteristic equation. So this is one of the things to check for. In that case, we're just going to multiply a by n as a modification of the what we would normally do and when we have a constant. And so we use this. We substitute this into our equation. The full equation with the minus 1 in it. So we have that here. We have this is, since this is x sub n plus 1, when we plug this in here, we have a times n plus 1. This is just x sub n, or z, I should say z sub n, and then z sub n minus 1. It's just a times n minus 1. Of course, the p and q is part of the equation. Then we just take the terms with an an in it, which is the p and the q. And we have this term here. Then we have terms with just an a in it, and that's p and minus q. And that equals minus 1. This is 1, right? That was one of the conditions. There's p plus q equals 1. So this an cancels with this, and then you get a times p minus q equals minus 1, which I've written down here. And then you can just divide. I switch the signs in the denominator. And then we can plug that into our, this is a, then Zn is n times a. So we have this here. And this was the complementary solution. This is the particular solution. So we have now the general form for a solution to our difference equation, but we were given two initial values, so we can use those to actually pinpoint A and B, which we'll do on the next slide. So let's use the initial conditions here. We have x sub 0 equals 0. We plug that into our equation. So we get a plus b times r to the 0 power, which is 1, and that equals 0. So we have b equals minus a. Then we use our second initial condition, x sub capital N equals 0. Here, you notice we get a plus minus a r to the capital N. It's the first two terms. And we put in n here, capital N for small n, and that equals 0. And then we solve for a. We get this here. Okay, and then we just go back to this and we can plug things back in. Since we know that b is minus a, these first two terms could be written like this here. I just brought down the third term, I guess I should say. And then we plug in a here. And I just carried this over. Then the next line is just we could have stopped here. This is just a little bit of a reconfiguration. I put this first, and I kind of wrote this a little bit more neatly here. Okay, so that's our final solution given the initial conditions. Example number 2, a polynomial forcing term. Here's our second example. We have autonomous equation. These are constants here. The coefficients are constants. However, our b of n is a polynomial. So first we solve the homogeneous equation using the normal technique. We get two roots, minus 1 and minus 3. And the complementary solution is a times minus 1 to the n plus b times minus 3 to the n. And neither root is 1. And we don't have a repeated root or a complex root. So this is a pretty straightforward solution for the complementary part. And what we need to do is find the particular solution when we plug this back in. And our table tells us to use a first degree polynomial, which we'll do on the next slide. We'll plug that in, and then we'll get a complete solution. Continuing with our example, we want to find a particular solution, and the table tells us to use a first degree polynomial because we have 3n here, so we want to mimic that. So a and b are constants. Plug that into here, so we have z to the z n plus 2 would be this here, then z sub n plus 1 is 4 times this. Then this is just directly z sub n plugged in here. And then we accumulate all the like terms, so we get 8an plus, and then these are the constants, 6a plus 8b equals 3n. So the coefficient for the n term, those should be equal. So in other words, 8a should equal 3, and then 6a plus 8b should equal 0 because there's no constant term here. And then we can solve this, right? It's two equations, two unknowns. So we get a equals 3/8, we plugged it into here, we get b equals minus 9 over 32, and then z sub n, just plug in a and b into this here, we get our particular solution. And then we put that together, so we have the complementary solution, which we computed on the previous slide, and then the particular solution here, and that gives us our answer. I didn't do it for initial conditions, but if we were given initial conditions, two initial conditions, we would be able to find A and B, but I didn't do that additional step here. I have several examples in this table where we have a clash and we need to use something other than the usual guess from our table earlier on in the lesson. So let's go through this. I didn't do the complete solutions, but just to highlight where the clash happens. So the first one here, we have this equation, and this is the complementary solution. So we have a clash here with this constant A and this constant here. So normally we would use A because there's a constant, but because of the clash with the complementary solution, we use AN. We have a similar problem here. Now the root 1 is repeated, but it's the same issue. You have this complementary solution with an A that clashes with the 4. They're both constants, so we don't want to use A. Since the root is repeated, we're going to use n squared, because we also have the problem of the clashing with the n here. So if we just want the an, we would fix the clash with A, but we would still have a clash with bn. So that's why we use n squared here. The next one, there's a clash. We would normally use an plus b because this is 4n. And then this b here clashes with the constant a here in the complementary solution. So we need to change this. We multiply by n. Then the next one, we have this equation. This is the complementary solution. And you notice that the 3n is an issue here. We normally would use a times 3n as the guess for the particular solution, but then that overlaps with or clashes with this. So we multiply by n. Then the next one is similar. We have this difference equation. This is the complementary solution. And normally we would do a3n. And there's a double clash here because if we just multiply by n, that'll fix this first part, a times 3m. And then we have 3n times bn, so you're going to have a clash even if you multiply by n. That's why you need n squared here. Then we have another one involving a trig function. So we have this difference equation. This is a complementary solution. And of course this clashes with this. So rather than just using our usual guess, a times the sum of a plus the linear combination of these two will be the normal substitution for the particular solution. But because of this clash here, we multiply by n. And then finally, this is the one we just did actually. This is example 2. So this is an example where you don't need to change anything. So we've already studied that. Okay, so as I said, I didn't do all the details here. I don't expect you to immediately see these were the solutions to these equations here. Some work is involved, but I'm just giving you those. And the main reason is I want to point out if you use the suggested particular solution from the table earlier on, you run into a clash for all these except for the last one. and then you need to either multiply by n or some power of n. We saw a couple of cases where we needed to up that, so we had n squared here as well as n squared in this one. Some takeaways from this lesson. A non-zero forcing term makes the equation non-homogeneous. That was the b of n term. The way to solve that for a linear uh, equation, and we were just looking at second order linear, but it'll work for higher order, is do we find a complementary solution to the homogeneous part, and then we find the particular solution based on the table that I provided earlier. So I say here we guess a trial solution based on the table. Sometimes that doesn't work, as we just saw in the previous slide. Sometimes you need to multiply that suggested solution by n or some higher power of n. And then you put together both the complementary and the particular solution. And if you are given initial conditions, as we had for our example number 1, you actually can find the constants and completely specify the solution. So coming up in lesson 6, which is the last part of our series, we'll talk about nonlinear. And what we had so far, the powers of x was just to the 1 power in every case. So if you start squaring it or taking the cube or cube root or anything like that, you're no longer linear. Y closed forms are the exception once the equation is nonlinear. Stable and unstable equilibria, attractors and repelling points, a derivative test that classifies an equilibrium without simulating anything, and then there's something called a logistics map, and we'll talk about that too. So if you like this, don't forget to give it a thumbs up and stay tuned for the final lesson.